today we're going to talk about mutually exclusive events. So previously we've talked about the intersection of two or more events, and we use the word and the word and means that we are indicating an intersection of two sample spaces. Today we're going to introduce a new word, which is the word or, which indicates a union of two sample spaces. Not an intersection, a union. So there's a difference. So we have a new word or words, and that's mutually exclusive. And what that means is this is when two events cannot happen at the same time. This is when we use or. The word and means that the two events can happen at the same time, whereas the word or means that the events cannot happen or occur at the same exact time. So that's what mutually exclusive means. So, for example, when a die is rolled, what is the probability of getting a 3 or a 4? Well, the sample space consists of the numbers 1 through 6. Well, if you land on a 3, that means you can't land on a 4. So that's what 3 and 4 are not. It's not an intersection, because if you landed on a 3, you wouldn't be landing on a 4, etc. To find that probability, we can see that you have 3. You can either land on 3 or a 4, and that's 2 out of 6 different possible outcomes. And so if we simplify this, it can become 1 over 3 as a simplified fraction. Now, we have a formula that helps us to understand this in situations where it's not so easy. What if the sample space is a bit larger? So if we use this formula here, it says if two events A or B are mutually exclusive, then we can say that the probability of A or B is equal to adding the two separate events together. So notice that the same probability that we just talked about can be found by adding the probabilities of each simple event. So what is the probability of getting a 3? Well, 1 out of 6. What's the probability of getting a 4? Well, 1 over 6. So now, what is the probability of, and this is a typo, it says 3 and 4, but it should say 3 or 4. We can add the two fractions, 1 over 6, and we get 2 over 6, or the same thing we had earlier. Now, let's talk about a situation where the two events are not mutually exclusive. So, for example, here it says, when a die is rolled, what is the probability of getting a number greater than 2 or an even number? So, if we think about this, the numbers that are greater than 2 are 3, 4, 5, and 6. Now, an even number here would be 2, 4, 6. So we have to include the number 2 as well. So that would be 5 over 6. That's the probability of getting a number that is either greater than 2 or it's an even number. This leads us to a second rule. Okay, another additional rule for probability. And in this formula, it says if two events A and B are not mutually exclusive, that means they could possibly occur at the same time, then we use this formula. The probability of A or B is equal to adding the two separate events together, but we have to subtract the intersection that occurs, the probability of A and B. There might be some overlap, and so that's how we have to subtract. So it says here, since it is possible to roll a number that is greater than 2 and an even number at the same time, these events are not mutually exclusive, like I said before. So let's take each individual event. What is the probability of getting a number greater than 2? Well, greater than 2 would be 3, 4, 5, and 6. That's 4 out of the 6. What's the probability of getting an even number? Well, that would be 2, 4, 6. That would be 3 over 6. But if these probabilities were added just like we did in the previous example, the probability of two outcomes, 4 and 6, would be counted twice. Once for being numbers greater than 2 and once for being even numbers. So you need to subtract that one that would be counted twice, those common outcomes. And so that's why here we have to add the two fractions, 4 over 6 plus 3 over 6, minus the two that are counted twice. The two that are counted twice are the numbers 4 and 6. And so therefore our final answer would be 5 over 6. Okay, so I just wanted you to see that there's two different ways of doing this. When it's a simpler problem, you can just write out the sample space and figure it out. But when the sample space is larger, then it becomes a little bit more complicated. All right, so let's do some examples on this. First, we want to just identify simply if something is mutually exclusive or not. A, it says a junior winning the election or a senior winning the election. Are these mutually exclusive or not mutually exclusive? Well, these events are mutually exclusive. There are no common outcomes. A student cannot be both a junior and a senior. So I'm going to just abbreviate this. I'm going to say this is ME, mutually exclusive. Okay? The letter B, a sophomore winning the election or a female winning the election. Well, these events are not mutually exclusive because a female student who's a sophomore is an outcome that both events have in common. It could be a female sophomore. And so this situation would be not mutually exclusive. And so I'm going to use red to represent that. So not mutually exclusive. C says drawing an ace or a club from a standard deck of cards. Since the ace of clubs represents both events, they're not mutually exclusive. So this would also be not mutually exclusive because the ace of clubs does exist. Okay? All right, so let's go ahead and do another example where we actually apply this situation. Okay, so here it says, Ramiro makes a playlist that consists of songs from 3 different albums by his favorite artist. If he lets his digital media player select the songs, and here says digital media player, let's just think of, your cell phone or wherever you listen to music. He lets his digital media player select the songs from this list at random. What is the probability that the first song played is from album 1 or album 2? Now, the thing to remember here is that these are mutually exclusive events, since the song selected cannot be from both album 1 and album 2, so they're mutually exclusive. So, if we look here, we need to find the total number of songs that we have. Remember, remember the formula? I'm just going to go ahead and write the formula first. So the formula was the probability of A or B is equal to adding the two together because they're mutually exclusive. So to do this, we always have to find the total at the bottom, right? Total in the bottom and what we want at the top, our desire. Okay, if we count up all of our songs, they add up to, let me write this, they add up to, we're going to add these, that equals 35. So there's 35 songs in total. And let's make album 1 to be A and album B to be 2. So how many songs in album 1? What's the probability of him getting first a song from album 1? Well, there's 10 songs in album 1, so that's going to be 10 out of 35, right? And now if we look again for the second scenario, for the second song, again, we have to put the total amount of songs at the bottom and how many songs in album B or album number 2. That'd be 12, correct? And so the probability that the first song played is from album 1 or album 2 is going to be 22. So we then combine these two and we get 22 over 35. Or about 63% chance. Okay? So this is for a situation where we're dealing with mutually exclusive events. Let's try one more example. Here it says the table shows the number and type of paintings Namiko has created. If she randomly selects a painting to submit to an art contest, what is the probability that she selects a portrait or an oil painting? So since some of Naomi's paintings are both portraits and oil paintings, these events are not mutually exclusive because we have some intersections here. So we're going to use the rule for two events that are not mutually exclusive. The total number of paintings from which to choose are 30. Okay, so if we add up all of them, we add up to 30. So I'm going to go ahead and make sure we know that. Total paintings, oops, let's change that. So total paintings is equal to 30. So let's use the formula that we've learned. So the probability of, selecting an oil painting or a portrait is going to equal each separate one minus the intersection. So getting the oil first plus the portrait second. Then we're going to subtract their intersections. So the probability of oil and portrait. Okay, we're using this formula because that's not mutually exclusive, and I should probably write that too. Not mutually exclusive. Okay. Okay, so let's find the probability of getting an oil painting. Well, remember, we always put the total at the bottom. Okay, so we're going to put the total at the bottom and what we're wanting at the top. So there are 30 paintings in total. Okay, how many of them are oil paintings? Well, we've got 1 that's a still life, 3 that's a portrait, and 1 that is a landscape. 2 that is a landscape, sorry. So what we're going to do is we're going to add those together. This plus this plus this, and that's going to equal 6. Okay, now let's do the portrait. What is the probability of getting a portrait? Well, the portraits would be all of these right here. We have to add them together, right? And that's going to be what? 10. And once again, we put the total paintings at the bottom. But now we have to see what is intersecting. What of everything is intersecting? Oh, if you see this little 3 right here, now I covered it up. But if you notice this 3 right here, it's being intersected. It's part of the oil set, and it's also part of the portrait set. Because of that, we have to make sure we subtract it so we don't count it twice. So we're going to go here, and we're going to make sure that we take that out so we don't count it twice. So then we add all this up, subtract it, and our final answer is going to be 13 over 30, and it's about 43% chance of this occurring. All right, and that is your mutually and not mutually exclusive examples.